So yet more identities to look at. And again, don't worry about memorizing them. It's going to be how we use them in the class that really is going to count. So here they are for today, the sum and difference identities that we're going to take a look at. We also are going to be working with, these ones are new this year, the tangent identities. Just in case you're looking, there is an error in the government exam sheet. I'll remind you about it, but so far that's the one I'm going to be giving you when we go to like quizzes and tests. But instead of multiplying, they actually put an add sign there by mistake. So I'll remind you about it, but this is the correct form in case you're wondering why there's a difference between this and the government one. I'm sure they'll correct it any day. Okay, so some of the patterns, we'll just talk about them to get going to help you use them a bit quicker. So when you're using the sign addition, with both sign, if it's positive here, it's positive here as well. And when it's negative here. So my math teacher used to say sine has the same sign. Just, I don't know, I guess that's confusing, but sine has the same sign in this identity. That's one of the things you'll notice, because cosine has a different sign. See, when it's positive, cosine becomes negative. When it's negative, cosine becomes positive. Okay. And then finally, when you do the expansions and you're looking at how to place these things, sine is expanded with a sine and a cos, and you get a turn. So the first item here, like we'll call that 1, the first thing appears in sine here, and then it appears with the cosine. So everybody basically gets a turn when you add them together. And then with the cosine, it's cosine gets both, and then the sine gets both. So that's kind of the way I'm going to be explaining it as we walk them out, because I've used them enough. It's sort of, you'll remember some shortcuts in your brain too that you don't have to always look them up. Okay, so sine of sine of 60 minus 45. So I'm thinking of the sine identity. So in my head, I know it's going to be a subtraction, and I know they're going to get one turn each. So it's going to be sine 60 cosine 45. Same sign. Now I'm going to switch them. Sine 45, cosine 60. And in the next one, this one is the cosine pattern that I'm looking at. So if it's a positive here, I know it's going to be negative when I expand it out. So cosine is going to get both. Change the sign, and then sine is going to get both. Okay, and then finally we have the tangent identity there. And the tangent identity is going to be this one that you're working off of. So if we just try to make the replacements, we'll have tangent pi over 3, the first angle, minus tangent pi over 6, divided by 1 plus, and we put both angles in here. So you are going to be expected to be able to expand the identities like we just did. You're also going to be expected to condense them, like go backwards. So let me show you what that would look like here. So in this first example, sine of 70, cosine of 20, you're going to get to know this pattern really well, but let's just do process of elimination to see if you're starting to remember any of these patterns. So first of all, is this a sine or cosine identity that you're going to be working with? Sine. Yeah, because they're different, right? So it's going to be sine, and I know it's going to have 70 and 20. But now I got to figure out, what do I do? Is it going to be the same, like added, or is it going to be subtracted? Yeah, they're added, right? It's be the same sign here. So sine of 90 degrees, which of course, remember what that is? Anybody? Yeah, it's 1. Right, that's one of the quick ones you should know right away. Sine of 90 is 1. So we can even cut that whole thing down to 1. Right here you would have had to rely on a calculator, but now that you have the identity to use, you'd be able to find out that that answer is 1. Okay, so try condensing the next one. Sine or cosine identity. Good. Keep going, see if you can work the rest out on your own. Okay, so it is a cosine identity, and it's going to be dealing with pi over 6 and pi over 3. But cosine switches the sign, so instead of being positive, they'll be negative. So I could write this as the cosine pi over 6 minus 2 pi over 6. So I have cosine negative pi over 6. Okay, and then the last one, this one, there must be a typo on this one. Let's just say, I'll have to make an update, but let's just say that this was supposed to be negative. Oops. So the tangent identity that I'm going to be working on is this one here. So it'll be the tangent of pi over 4 plus 3 pi over 4. So that's the tangent of pi. Okay, so let's take a look at cosine of x minus pi over 2. And if we simplified this, what would we end up getting? So try simplifying like you did last day. Expand out the identity, and then use the exact value at pi over 2 to see if you can figure out. This will simplify to something else, so see what you get. So you should have sine of x if everything's simplified the way it was supposed to. I'll just make a quick change on this. Put it in trig mode. And let's look at those two graphs so you can see x minus pi over 2. So it does look like the sine graph. So if you think about it from your transformations point of view, y equals cosine of x. If I shift it to the right, then it's going to end up starting, this will be the start of the graph right here if I move everybody over. So if it starts there, that's like a sine graph now. So that's one identity that you can think of is now if I want if I want the sine, I can just shift the cosine over by pi over 2 to the right. Did anybody have a chance to work out the second one? Okay, I'll give you a second there. So with the sine graph, I'm going to pair them up one at a time. So sine, cosine, and the sine will be the same. Then this time sine is going to get theta, and cosine is going to get pi. So if I go through these, that's a 0, and that's a negative 1. So what I'm going to end up with is the negative sine of theta. So if you look at the regular sine graph, and I compare that to the same graph, but I shift it over by pi, then this says it'd be the same thing as a reflection. So there, now you can see the reflection against it. So it is actually the same, even though the graph shows it instead of the algebra. Now the next set of identities that you have, and yes, we are at the end of identities. that's the end of them for us. We're going to use them now, but this is the last on your list. The next set, they all come from these ones we've already just talked about. So I'm going to show you where they come from. They're also provided to you. But what fun would it be if I just gave you the answer, right? So cosine of 2a, I'm going to call this cosine of a plus a instead. And then from here you're going to see how we build up the identity. Let me just make that neater. Cosine of a plus a. So expanding it with the identity, I get cosine of a times the cosine of a minus the sine of A times the sine of A. So that's going to be cosine squared A minus sine squared A. And that's one of the double angle identities. So we're calling it double angle because the angle is multiplied by 2. And we're trying to work out other ways that we can simplify those sum and difference identities when we use those. So there's also some other ways that we can then take advantage of this. Last day we talked about how if we have sine of x squared plus cos squared x, that's equal to 1. So I know that sine squared x is going to be equal to 1 minus cosine squared x. I'm going to make that substitution into here. So I'm going to get another identity, cosine squared A minus 1 minus cosine squared A. And that negative will make this a positive cosine, so then I'll have 2 cosine squareds and a negative 1 there. Okay. And that's the identity that's right here. So far these are the two that we got from just simplifying using our identities. And if I go back to the Pythagorean identity we did last day, cosine squared is 1 minus sine squared. And I'll make that same substitution here this time. So 1 minus sine squared x minus sine squared x. So 1 minus 2 sine squared x. And that's how you get the last one. I guess, of course, in this case, it's an A that we're using. So I might as well be consistent. One just bit of housekeeping. I noticed that some people were doing some of their identities in their homework and things like that, and they were going like this. You wrote it a lot neater, I'm sure. Cosine squared equals 1 minus sine squared. Don't drop the letter off like that. The letter should still be there, so it should be letter in your problem, or theta, whatever it was. Don't be sloppy about it. Write the letter in, not just the function you're using. Okay, so the other identities happen the same way. If I was to substitute this as sine of A plus A, then out drops another identity for us. So sine of 2A is 2 times sine A cos A, which is a little surprising because you're multiplying those two functions together, but you end up with just 1. So y equals 2 sine x cos x. And sure enough, it looks just like a sine graph that's been, the period is in half. It goes from 0 to pi for one cycle. And as well, if we substitute A plus A into the tangent addition identity, then you'll end up with this simplified form as well. Okay, so we want to be able to work on those double angles as well. So it's very similar to what we just did, only there's some new forms you're working with. So I'm going to have you try these ones here. I'm going to give you a bit of a head start, and then I'm going to catch up. So just one thing that I do, maybe you have a better suggestion for me, but one thing that I do when I'm working is I figure out which, like now once I know which identity I'm using, I figure out what I'm doing when I move in that direction. So for example, I'm going from sine of 120, I'm starting here on this side of the equation, I'm moving to the other side. So what happens to the angle is the angle, it's halved. It used to be 2 A's, it's now only 1 A. So that means when I rewrite it, it's going to be 2 sine of 60 cosine of 60. Okay. So same thing here, when I'm moving across, I'll look at this identity and I'll decide when I move across this way, it started as 2 theta, it is now just a theta, so it was halved as well. It's not always going to be halved, it depends which way you move on this identity. But for now, that means half of it is going to be 45. So I'll have 2 cosine squared of 45 minus 1. Okay, so the same pattern applies. If you like that technique to help you figure it out, it's going to get a little trickier. I'm just going to do one of these ones with you. Let's pick this one here, just to give you some heads up. The identity I'm going to be working with, I'll just write it above, so it's sine 2 theta equals 2 sine theta cos theta. This time I'm moving in a different direction. There's going to be more things I'm working with here as well. So what happens when I move this way is the angle used to be theta. It's now 2 thetas. So it's going to be doubled. So I know that the angle that is 3 theta here is going to be 6 theta when I'm done. But the other thing that I have to take into account is that we didn't talk about this number in front. It wasn't used. It was just a 1 before. But now it's not a 1. When I go from here to there, it's halved, right? It was a times 2. Now I'm going times 1. So that number 2 will become a 1 as well. Like one favorite type of government exam question was something like this, right? Is if I mix everything around on you, can you figure out how it still applies to the identity? So these ones are halved. And this one is doubled. Sorry, did I say it backwards? I did say it backwards. This one is doubled, and this one is halved, right? So that's what I want you to practice, is think about how it works in the pattern when you do it. So I'll let you work through the rest of those ones there. I'll catch up. Okay, so I'm going to, looks like everybody's been, a lot of good discussion in there. Let's catch up here. So in this identity, I'm moving in this direction on that. So what I'm doing is going from 2 theta to theta. So it's half of what it was before. So it's going to be cosine pi over 3. The next one, again, moving in this direction, I started with a theta. I now have a single theta. So I'm halving the angle. So cosine 8x becomes cosine 4x. Sorry, 1 minus 2 cos squared. I forgot the identity in there, and I did the same thing here. I guess I just got a little excited. Okay, so this time we're going in the other direction. It's not telling you which identity to use, but I'm hoping at this point you're starting to recognize which one makes sense. Here, what I'm going to try and plug it into is a cosine 2 theta. So why don't I just put it in the margin here? Cosine 2 theta is 1 minus 2 sine squared theta. So when I move, the way I'm going is this way. The angle starts as theta. It becomes 2 theta. So that means I'm going to double that angle. So now I'm going to have cosine of 240 is what it's equivalent to. Yes? Because I made a mistake. That shouldn't have been cosine, that should have been sine. The identity, I didn't use the correct, see the identity has a sign in it and I put cosine down. Okay, so in this next one, the identity that I'm going to be trying to line it up to, we talked about this, but I'll do this one real quick. This time I'm moving in this direction, which means the angle that I started with is theta, now 2 theta, so it's going to double. So I'm going to end up with sine of 6 theta when I get to the other side. Now this is going to come up as something that we have to do, so I'll highlight it again to you. The number in front there in this pattern was a 2. It's now a 1. So I have to divide it by 2, or times by a half, either way. But you'll see, especially for those of you who might have gotten this far, you have to follow the pattern with an extra step there. Otherwise, you won't have the right answer. So I'll show you some techniques when we get to it. This one might frustrate you because it looks so much like what you want that sometimes it's hard to think, what do you do with it? So what identity does it look closest to? Yeah, cos 2 theta. But it's cosine of 2 theta is actually the cosine squared theta minus sine squared theta. So that's not what I want. I don't have that there. I have sine minus cos. They're backwards. So does anybody know how you're going to make it unbackwards? Yeah. Multiply by a negative. Yeah, so multiply by -1. So this will be negative cosine of 2 theta. If I multiply by a negative on everyone, then I'm going to end up with negative cosine and positive sine, so I'd get sine squared minus cos squared. Sine squared minus cos squared is the negative cos of 2 theta. Put a negative on times by -1 on both sides. Okay. So there's a couple ways you can approach the next question. I'm going to show you with the pattern, and then we'll talk about another one as well. The identity I'm going to be looking for is the cosine of 2 theta is 1 minus 2 sine squared theta. So if I try to apply this pattern, I'm moving in this direction. So that angle that starts as a theta is 2 theta, so I know it's going to be doubled on that angle. But then the thing that happens when I move across the other side, normally there'd just be a 1 in front, but this one here has something else to it. It's going to be, I have to factor this out in order to see that pattern better. So if I factor out the 4, now you can see the 1 and the 2 that were supposed to be in there, right? So this one is going to be, angle is doubled. That 6x is going to be doubled. So it's going to be 4 times the cosine of 12x when we're done. So the question is, why did... Because it's really messy over here, but it's this is the identity that I'm putting it back into, right? So I'm starting with a pattern which matches up to this identity, right? The sine squared here is the sine squared there. When it moves across the other side, it's going to become cosine. That's how it turned into cosine down at the bottom here. Okay. Yes? That, whenever you have a function like the brackets in here, so you were thinking I should factor that 6 as well as part of this? Yeah, that function, it's like an atom. It gets to hold on to that there. It's in our terms, it's like the Greeks thought of. It's indivisible. You can't pull that apart and factor it out. It's stuck inside that function. So, like if you had something that was, let's say 5 plus 10 sine of 15x. As tempting as that might be to pull a 5 out of everybody, you can only pull the 5 out of these two, not both. Why is it 12x? Because the pattern that I'm working with, I'm starting on the right-hand side and going left. The angle gets doubled when I move that way. We started with 6x, now we have 12x. Okay, so this one here, this should be a lot simpler for you now. This is like last day. We're going to go back to that idea of using these identities to simplify stuff down. So in this case, 2 sine x. The really great thing about the double identity for sine 2x is there's only one choice. So I can change this to 2 sine x cos x. which means all I'm left with is 1 over cosine, which is better known as the secant of x. So you try to simplify the next one. Think about strategy. The cosine of 2x is always tricky because there's 3 choices. But if you think about strategy beforehand, there's usually one obvious one to pick. So I'll tell you the strategy in this one if you don't find it first, but give it a try on your own. So did anybody figure out which of the identities? Let me pull up here to where we were. So top, middle, or bottom, which one? Yeah, the bottom in this case is going to be the easiest one. The middle one will work, but you have to do a little bit more math to make it work. Here's the hint here. Plus 1 is not a trig ratio. We want to get rid of plus 1, and we want to be able to work with just trig ratios. So how do you remove plus 1? You minus 1. So you're looking for something that can minus 1. And that's how I know that this identity is the one that I'm most likely going to want to use, because it's got a minus 1 in it here. Okay. So that's the substitute I'm going to make. Is I'm going to call this 2 sine x cos x over 2 cos squared x minus 1 plus 1. So then those things, of course, are gone, and I'm just left with 2 sine x cos x over 2 cos squared x. So out of my way, and I'm left with, yeah, sine over cos, which is also known as, yeah, good, so this is tangent of x. Now, keep in mind that practice is certainly something that's going to make this more familiar and helpful to you. So this is about the breadth of what you're going to be expected to do in one lesson, right? So just in those last 30 minutes, you've had to do the entire breadth of what you're responsible for. It'll be better once you practice a little. The last thing that these identities help us do is to find exact values for things that you might not, otherwise be able to do. Like, for example, 165 degrees. The technique looks like this. I want to turn 165 degrees into some sort of addition identity. Or I could do subtraction as well. If subtraction is what you'd rather do, then you can also do subtraction. But most people, adding is usually easier to think of than subtracting. So let's try adding here. Can anybody think of 2 special angles that I could add together and get 165? Leo, yeah? 120 and 45, yeah, that'll work. So those are ones that we could figure out from our last unit, right? Now, 165 I can do because I'm going to split it. I'm going to call this cosine of 120, cosine of 45, plus the sine of 120, and the sine of 45. Minus, yeah. Just testing you. Okay, so quick refresher here. This is the triangle that you're looking for. And then the other triangle, of course, is this one. So if I wanted to get the cosine of 120, 120 that has my reference angle of 60, good. So reference angle is 60, will it be positive or negative? Negative or positive?
Positive.
Positive, negative?
Positive.
Well, 120 is in which quadrant? Second quadrant, good. We all agree on that. Cosine is? Negative, yeah. It's backwards, right? Second quadrant means you're going into the negatives. So in this one, we're going to have negative 1/2. For the cosine of 45 degrees, that's going to be right out of the triangle. It's going to be 1 over root 2. And sine of 120, in quadrant 2, sine's positive, and the sine is going to be root 3 over 2. And sine 45, that's 1 over root 2. Okay, so at least I have a common denominator. So I'm going to have negative 1 over 2 root 2 minus root 3 over 2 root 2. And we can assemble that, call it minus 1 minus root 3 over 2 root 2. So that's the exact value for 165 using the other angles we had. So you guys are going to try it now with the tangent of 11 pi over 12. First, try to figure out what two special angles could add to 11 pi over 12, and then go from what you did last unit with your special triangles. So did anybody find the angles? 2 pi over 3 is one of them, yeah? I think that's the other one, yeah. So what you're trying to figure out, your special angles are all the ones like this, pi over 3, pi over 4, and pi over 6. So you're looking for some combo there. So you could try taking out like the biggest one, biggest amount, and see what's left over. So for example, 5 pi over 6 I could try doing. 5 pi over 6, that's 10 pi out of 12, which is going to leave me with 1 pi out of 12. So that didn't work for me because 1 pi out of 12 is not going to help. So let's try 4 pi out of 6, which I know that's 2 pi over 3. But let's just see, that's going to give me 8 pi over 12. I guess I'll put the leftover column here. If I take 8 pi out of 12, the other one's going to be 3 pi out of 12. And those ones work for me, right? Because 8 pi over 12, that's 2 pi over 3. And this one is pi over 4. So I could rewrite it with those two angles. Those ones work. So that's what I try to do usually, is I try to figure out what can I take the most out of it from, and then I keep backing off a little bit until I find one of the angles that's going to work. You can try guessing and checking. With a little practice, you'll get better at the guess and check. So I'm going to rewrite this then as the tangent of 2 pi over 3 plus pi over 4. Oh my. Pi over 4. And using the tangent identity, it'll be tangent 2 pi over 3 plus tangent pi over 4, all divided by 1 minus tangent 2 pi over 3 tangent pi over 4. Okay, so there's an easy one here. What's the easy exact value? Yeah, pi over 4, that's one that hopefully you remember. It's this triangle over here where tangent equals 1. So I'm going to get rid of that one. It equals 1. Equals 1. It's probably not a bad place to do a little review. 2 pi over 3 is over here. Pi over 3 is the reference angle. So will tangent be positive or negative when I'm done? Yeah, it's a negative in quadrant 2. The reference angles pi over 3 are 60 degrees. That's this one. So if I go opposite over adjacent, I get root 3 for my reference. Oops, sorry. So let's just say the reference here was pi over 3. The tangent of pi over 3 is root 3. So we're going to have negative root 3 since we're in quadrant 2. Now that's incredibly messy, so let me just put together my fraction here. Negative root 3 plus 1 all over 1 minus, it'll be negative root 3, so I'll make it plus.